All right, so this lecture is on the magnetic force. We're finally on the fourth unit here. The first three objectives in objective D.
Mahmood's in the waiting room.
Okay, thanks. There you go. Yep. So the first objectives in the magnetism unit. That's what we're looking at here. Let me pull up the objectives real quick before we move on. And that would be these first ones here. So magnetic fields. First, we're looking at the forces, the force on a moving charge in magnetic fields, and then afterwards we'll see how moving charges produce magnetic fields. Kind of like we did with electricity, right? We learned a quick equation to learn the force, the electric force on a charge, F equals Q times E. And then it took a lot longer to figure out how these charges produce electric fields. So this is the easy part. So you're going to be able to calculate the magnitude and the direction of the magnetic force. We just have one equation for that. And then, that's going to involve the right-hand rule. And using the right-hand rule, you'll be able to tell the direction of a magnetic field from information about the forces experienced by that moving charge particle. All right, so let me switch back to the paper. Okay, so the magnetic force. So a particle in a magnetic field is gonna feel a force. Whoops. What do we know about, or what properties is a particle going to have, maybe from the reading or from what I said earlier, in order to feel a magnetic force? Is any old particle going to feel a magnetic force if we put it in a magnetic field, or there's two kind of properties that particle needs to have? Anybody? What needs to be the case for a particle to feel a magnetic force in a magnetic field?
Does it have to be moving?
It does. It has to be moving, yes. A particle that's stationary or standing still at rest is not going to feel a magnetic force ever. And what else?
Does it have to be charged?
Yeah, and the other thing, it's got to be a charged particle, right? A moving charged particle in a magnetic field is going to feel a force, right? If it's not charged, it won't feel a force. If it's not moving, it won't feel a force. All right, the equation, or the force it's going to feel, this is the magnetic force here, FB. Capital B is the symbol we use for magnetic field, while capital E is electric field. So FB is the magnetic force. And it's going to equal the charge, Q, times the velocity of the charge crossed with the magnetic field strength itself. So Q V cross B, that's the equation for the magnetic force. This is the charge's velocity. And B here is the magnetic field strength at the point where the particle is. And you have a B field, and the B field we can think of right now is a lot similar to the E field, here we go, here's Ellie, to the electric field, right? It's a vector that occurs at every point in space, right? It's got a strength and a direction at every point in space, just like the electric field does. All right, let's see. That's okay. So let's compare this real quick before we go on and talk about how we take the cross product of two vectors. Let's compare it real quickly to the electric force. Do we remember what the simple equation for the force, the electric force on a charged particle is?
Yeah, K Q1 times Q2 over distance squared.
That would be so you're right, that's the electric force between two charged particles, right? But So, but what about if we just have a, and that's true because we can think of that as one of the particles is the source charge that produces an electric field, and then the other one is the test charge that would feel the force from that. But if we just have a generic electric field and we put a charge in it, what's the simple equation for the force on the charge?
KQ over R square.
That would be the KQ over R squared. So that would be the electric field, right? That's how you would get the electric field from a point charge. Right, but we could have any electric field we want. And if we put a test charge in that electric field, how are we going to know what the force on that test charge is? If I have an electric field E and I put a charge Q in the electric field, what's the
Electric field divided by Q. No, times Q.
times Q? That's it. That's right. That's right. So the electric force, right, is, let me write it over here. The electric force, Fe, well, that's a vector, but it's just the charge times the electric field at that point, right? So if you know the electric field, very easy to get the force on a charge, right? You just multiply by the charge itself. So I want to take a minute to compare these equations, right? The force that a particle feels if it's in an electric field versus the force that a charged particle feels if it's in a magnetic field. So what's different? What's different between these two equations? Well, what's in one of these equations is not in the other one?
The magnetic field strength and the drift velocity, I think. Or would it be the charge velocity?
It's not the drift velocity, it's the velocity of the moving charge. Right. So that's the difference. So yeah, there's one difference is that we have a magnetic field instead of an electric field, right? But the other difference here is this V, right? We have the velocity. We have the velocity of the charged particle, right? And basically we can see now why the particle has to be moving, right? If your velocity is 0, well, you're multiplying by 0, right? So you're gonna get 0 magnetic force. So that's the first important difference there, is that the velocity of charged particle, we'll say it matters for magnetic force, but not for electric. And then the other thing, so if we talk about the direction of the force, right? If we look at the direction of the force, the electric force is pretty easy, right? If we have a positive charge, at least, the electric force is just going to be in the same direction as the electric field, right? The electric field is going to point in the direction that a positive charge feels a force. That's something we know and have been working with all year. But we can't say the same thing over here. The magnetic force isn't just going to be the same as the direction of the magnetic field, right? Because we have this cross product in here, the V cross B. So, but the other thing that's different, the electric force is in the same direction as the electric field, but the magnetic force is never in the same direction as the magnetic field. And actually, as we're going to see when we quickly go over cross products in a minute, the magnetic force is always perpendicular to the magnetic field. Okay. So while with the electric force, or with an electric field, is just going to produce an electric force in the direction of the field, magnetic field's a little bit more complicated. The magnetic force is always going to be perpendicular to the magnetic field. And as we'll see when we look at the definition of a cross product, it's also going to be perpendicular to the way that to the velocity, to the direction of that the charge is moving. Okay, so questions so far? As we go through this magnetic stuff, I want to try to draw there's always an analogy between the magnetism and the electricity, right? This is the old electricity stuff that we know. This is the new magnetism stuff that goes, that's analogous to it. Do you remember cross products and the right-hand rule if you took AP mechanics?
Yes, I think.
Yeah, good. Maybe you do, maybe you don't. Why don't we probably need to brush up on it anyway if we do, right? And we haven't done a lot with dot product this year, but back in kind of the earlier part of the course, we did briefly talk about dot products, right? There's two ways to multiply vectors together, right? The way we already learned a while back was to take the dot product, right? And the dot product of any two vectors is a scalar, right? If I had two vectors, A dot B, and I take the dot product of these, I get the magnitude of A times the magnitude of B times the cosine of the angle between them. That's one way to multiply two vectors together. The other way to multiply two vectors together is called the cross product. And instead of coming up with a scalar, the cross product of two vectors is another vector. All right. So since it's another vector, it's got a magnitude and a direction. And for now, we're just going to look at and see how to calculate the magnitude and how to calculate the direction. The magnitude, when we take the cross product of two vectors, and the dot product is written like this, right? With a dot, the cross product, A cross B, where A and B are both vectors, the magnitude is the magnitude of A times the magnitude of B times the sine of the angle between A and B. So that's different than this, right? With the dot product, if the two vectors are perpendicular to each other, the cosine of the angle of cosine of 90 is 0, and we have 0 for our dot product. Right, the dot product was always bigger if the two vectors are perfectly aligned or parallel. The cross product is exactly the opposite. If the two vectors A and B are pointing in the same direction, so the angle between them is 0, well, sine of 0 is 0, and we would have 0 for the cross product. The cross product is going to be the biggest when the vectors are perpendicular to each other, right? Because if you have 90 degrees, sine of 90 degrees is 1, and then your cross product is just going to be A times B. All right. So this is something that you should know, because you'll see, if you go forward in physics and other sciences as well, you'll see cross product of vectors come up again and again. And the magnitude is just the magnitude of each vector times the sine of the angle between them. And I'm going to put here it's largest when A and B are perpendicular. And just to analogize up here, this is largest when A and B are parallel. All right. So the last thing we need to say about the cross product, so we can figure out what the well, so let's also say this though, the magnetic, that means the magnitude of the magnetic force, right? So that's magnetic force magnitude is just going to be Q times the magnitude of the velocity times the magnitude of the magnetic field. times sine of the angle, right? And just to remind us, this angle, just the angle between the two vectors. So finally, the direction, right? The direction of these cross product vectors. So what we're going to end up having is, what we'll see is that the direction of this vector is going to be perpendicular to both of these. Right? When you take a cross product, the resultant, the vector, is always going to be perpendicular to both of your input vectors. All right, so the magnetic force is always going to be perpendicular to the way the charge is moving, and it's also always going to be perpendicular to the direction of the magnetic field. So we're going to need to think in 3 dimensions a little bit here. And the way we figure out the direction, we use what's called the right-hand rule. That's how we'll figure out the direction. All right. And it's easier to show you, and I'll show you using my right hand up here. But when you're taking the right-hand rule, point your fingers. Let's write it out here. Step 1, point your 4 fingers in the direction of the first vector. We'll call that vector A, right, like we did here. So 4 fingers like this, right? And then you point then you're going to curl your 4 fingers towards the direction of the second vector. So the direction of vector B. And if you do that, then your thumb will point in the direction of the cross product. A cross B. All right, and that's the right-hand rule. All right, so let's try that out and see what that means. So let's say, for example, let's say I have my vector A is up on the page like this. Vector B, my pen's already going, we'll say is to the right. So what direction is A cross B? So importantly to remember, it's the right-hand rule, not the left-hand rule. If you use your left hand instead of your right hand, you're going to get the opposite direction. Okay. So let's see. A is upwards. So I'm going to point my 4 fingers in the direction of A. All right, straight up like this, towards the top of the page. B is to the right. So I want to curl my fingers in the direction of B. Now I can't because my hand's not facing the right way, right? So I've got to go like this if I want to curl my fingers in the direction of B. Right? And now my thumb will point in the direction of the cross product. My thumb now is pointing straight down into the page. Right? So that'll be the direction of the cross product. I've got to go A, point fingers towards B, and then my thumb is pointing down into the page towards the cross product direction. So And the way we write, notate into the page is this symbol here. All right. Questions about the right-hand rule? Does that make sense? Does that example work for you? So then we would just generalize that, right? And we would say, so if a particle is moving, we could say the upwards direction is the velocity of a particle, the magnetic field is to the right, then the force on that particle will be straight into the page. You can kind of always tell when somebody's taking the AP physics test if you walk by the room. There's always kind of doing this with their hands, trying to figure out what the right hand rule is.
They also do the 3-finger thing.
You can do it. Yeah, that's another way to do it, right? You can do it the 3-finger way if you have. Yeah, that's another way to remember. Whichever way works for you to remember it, that's fine. I don't like the 3-finger way as much because then you have to remember which finger goes first and which finger goes second. But
Oh, I see.
but that can work too. For me, the easiest way is I remember if I point, I remember it this way. If I point my fingers in the first vector, curl them towards the second vector, and then your thumb gives you the resultant. So that's really all we need to know in order to figure out what the magnetic force on any charged particle is. All right, this is the big equation here. And remember, this has Q in here. So if we have an electron or a negatively charged particle, then we would have to take that minus sign into account and switch the direction of the force. So let me end there for the lecture today, unless there's any questions about what you've seen here.
Can you move the page up?
Yeah.
Thank you.
All right. So I'll stop recording there.